first of all, thank you for joining. During this presentation, we will try to create a small effect system. Okay, so it's an experiment that I want to try with you without using any monadic style, but only try to using what I call, not I call, but also a lot of other people in the research area call capability passing style, which is in the middle between monadic and direct style maybe, or maybe it's direct style. It depends. So I am an enthusiastic Scala lover for a long time right now, but I always do it in my spare time. Okay, so be gentle with me. It's also my first conference. And if you are asking why this background is clearly to confuse you from all the stupid things I will say during the presentation. And I will start introducing some basic concepts about functional programming, just to be sure that we are on the same page. Okay. So first of all, why we love the functional programming? Well, because of the substitution model. So we can substitute the function with exactly with its results, and doing so enable us for local reasoning, which is very interesting property, because we can know what the function does only looking at the signature. Okay, and for example, pure function, which are function that adheres to the substitution model, are a very nice property. They are very easy to refactor, for example. And so, however, as you know, every time you try to integrate with a database or to call an API, you know that we can't avoid having to deal with functions that are not pure, okay, that basically add side effects. And we will use this small example during all the presentation, okay. It's very tiny, but in this tiny example, we have non-determinism and error handling. Okay, so we have a function that models a coin toss, but we have a gambler that might be too drunk and lose the coin. Okay, so it uses basically the random from the Scala library and the exception. And why we don't like functions like that? Because you know, they are not pure. So if I run the function 2 times, I can have different results. And this is a problem. And why we have different results? Because of side effects. So what is a side effect? A side effect is an unpredictable change in a state of the world outside our function. Okay, our function fails to be pure because it accesses to that external state. Okay, however, even if side effects are not good, okay, somebody in another presentation I saw recently, they defined them a bug, okay, but we have to deal with them. So the best thing we can do is to track them, okay, and to try to push at the boundaries of our system, okay, creating a sphere, a ball, in which we can, again, using the substitution model. And that is exactly what the effect pattern tries to do. Okay, so using the effect pattern, we want to track and control effects. And the 2 properties that we have to satisfy to adhere to the effect pattern are, first, we need a type that should list all the effects that the effectful computation uses, and clearly the result. And the second, we have to separate the description of the effective computation from the execution. Okay, doing so, we start to have again pure function, at least in our blob, in our sphere, and we can again use the substitution model. An effect as this form, usually as this form. So we have a type F. It's a box, okay? The F is the effect, in fact, and the A type is the result of our function. Popular effect in many programming languages are the option effect that is modeled the conditional lack of the value, okay? But once we start using effects in this form, we encounter a little problem that effects for computation are not composed so easy composable as they was the function that are not using effects. So we need, for example, using category theory and monads and FlatMap basically to compose those functions. An effect system does exactly this. So an effect system is an implementation of the effect pattern. It puts the side effects in the box, and usually it replaces all the side effecting parts of the standard library, here the Scala standard library, with putting those side effects inside the box effect, and it provides all the structures to manage the execution, the late execution, the deferred execution of our effect for computation. So just to sum up, side effects are bad, effects are good. We have many effect systems in Scala, as we already heard in the previous presentation. We will briefly introduce 3 of them: Cats Effect, ZIO or ZIO, I don't know the correct pronunciation at this point, and KIO, which is a new one. And we start from Cats Effect. Very brief introduction, Disclaimer, all the 3 are battle tested, super performant, and I want to substitute, to be a substitution of one of these effects because it might only an experiment. So, end of the disclaimer. Cat effect using the IO type to describe an effect of computation that may access to side effect, It's a Uber effect. Why we call it a Uber effect, or I call it a Uber effect? Because it does not list the current effects that are actually accessed. So a drunk flip rewritten with cats has this type, return type, which means that basically, if we look only at the signature, the drunk flip had some side effects inside. It's an effect for computation that may encounter some side effects, but we don't know which one. And it's an Uber effect also because we have to handle all the effects at once. So in some point of our application, in the boundary, of our application, we have the handler, what we call the handler, which is the preferred one, which is extending the IO app simple or the IO app class, or we can run unsafely as it's a possibility, not the preferred one. And this Uber effect uses monads. As you can see here, we are using for-comprehension, just to have a little syntactic sugar, to avoid having the map and FlatMap. And clearly, as the effect pattern says, that this junk flip is only a receipt, of the computation. We need exactly the handler. If we want, we can make the effect visible in the type returned in the type, in the signature of the drunk flip, for example, using the tagness final syntax, But we are making the cognitive load even higher to understand what's going on here. No? So ZIO or ZIO introduces augment, add other. With other type parameters, the Uber effect, with the type parameters E, which is the type of the errors that effect of computation may fail with, and R. The R is the intersection of all the effects that are accessed by the effect of computation. It's still just to return to the cat effect can only fail with trovables, Whereas here, ZIO, we have basically any custom type that we can use. It's still a Uber effect because, as we saw in a minute, we have to handle all the effects at once. But if we see the drunk flip function written in ZIO, we started to see that the effects accessed are pop up directly in the return type. So here we have the drum flip that accesses only the random effect that can fail with a string, and it produces a string in the happy path. Okay, as we said, it's a Uber effect. So again, we need to execute all the effects only at once. And if we have only, more than one effect, we can use intersection type as the the binding for the R type. Okay. The third effect system we want to briefly introduce is ZIO. ZIO has a different approach because implements an algebraic effect style, which means that effects are directly listed in the return type of our function. Okay, and they can be handled once a time. So we can handle every single effect separately from the other once. Okay, and this is briefly what algebraic effect means, or some of the property of the algebraic effect systems. And if we rewrite the drum flip function with ZIO, we obtain this signature, which means that the drum flip returns a string, but also need an abort effect, which is the effect used to fail a computational function, and uses an I/O, which is required by the random. Okay, so it may fail in some way that we don't know exactly. Okay, and this is exactly what the I/O means. But even though we have an algebraic effect approach, we are still using monads. Okay, in fact, the minus type alias is a type alias for a monad, the ZIO monad, and so we need the for-comprehension. Okay, also in this case. But we have introduced a new possibility, which is the fact that we can handle each effect separately from the other. So if we want to handle only the abort effect, we can, and we obtain a new recipe, a new program. So this is still a description in which we have the result, which result is the header in the ZIO word, okay? And we still have to provide the I/O effect, the I/O handler, okay? And it's quite interesting, this approach, because changing the handler can change dramatically the semantic of our program without changing the recipe at all. For example, changing the handler, we can have an handler for testing that make non-determinism fixed, okay, with a fixed non-determinism or something like that. But all the three effect systems that we saw use monads. So what if we want to try to build an effect system without using any monad? So without having to use for-comprehension, so FlatMap and maps, is it possible? Well, and clearly we want to have those nice properties of referential transparency, local reasoning, and so on. Okay, is it possible? Well, we can try. And we can try to build a small prototype for the drum flip function to execute the drum flip function. We need, as we saw, the non-determinism and the possibility to fail with an error. And so we define, first of all, the random and the rise of E. Random generates a random Boolean, and the rise of E. The capability to fail with error of type E, and what we are going to build is in algebraic effect style. So we, as a ZIO, okay, we adhere to that type of effect systems. So first of all, we need to provide an implementation, okay, of our effects. Basically, here we are implementing the random, and the random uses under the hood the Scala random. And we call that implementation unsafe because we don't want anybody, any pieces of code to use this unsafe, because it does not implement the effect pattern, because the effect here is a side effect. It's not tracked. It doesn't even return a recipe. It does run the effect. Okay. So we need to build a DSL, okay, that brings back our effect system to the effect pattern. So let's add to a random object next Boolean function that needs, okay, an instance of the random effect. Okay, but remember the random effect is private, so nobody from the outside can provide this instance. So how we read this method is to generate a random Boolean. We need this capability, okay, effect or capability. Okay, and what we obtain is a Boolean that needs this capability. So we are producing a recip. So we are still inside the effect system pattern. Okay. If we create also for the rise, and we are going to see it in a moment, the same setup that we made for the random, we can rewrite the drunk flip function, okay, using our small effect system. And as you can see, we are not using any FlatMap or map or for-comprehension at all, and we're still having a recip, okay? What should surprise you is this thing, okay? Because as we just see, the next Boolean returns a Boolean, but it needs a random, okay, an instance of random. But here is the variable is treated as a Boolean, okay? Why is it possible? Because of context function. Context function was a nice addition of Scala 3, okay? Kotlin has something very similar with context parameters. And basically, they are just fancy anonymous function that has only implicit context parameters, okay? So using context function, our drunk flip method or function has this type, which means it returns a string if we can provide, okay, implicitly all the given variables. Listen here, okay? And this is straight Scala syntax, okay? No macros, no, okay? It works like this. So using the Scala compiler behind the hood is surrogating a new type for you, which is context function n, which is very similar to to function n, okay? And it's really useful when you have to understand what's going on under the hood. But for this presentation, it's only a matter of fact. So now we have how to express a recipe. Okay, we want to we have the implementation using directly the side effect. We want something that glue up those two things, and so we want to implement our handler. Okay, here we are implementing the handler for the rise that does exactly this. So taking a factorial computation that may fail with an error of type P, it creates, okay, exactly what does the random, okay, effect that we saw in the previous slides. It creates a given variable, the unsafe one, and it provides to our program, input program, okay? And what we here we are returning, we are treating the error and the result type as union type, as a union type. But we can see that changing, for example, the handler, we can radically change the semantic, because here we are handling the error type as an either. Okay, not as an union type, okay, anymore. Just implementing a new handler. Okay, so since we are implementing algebraic effect, we have to adhere to their properties, their constraint, and in fact we are doing this because we can run only the rise effect, and what we obtain will be a new program, a new recipe, which still need the capability, the random capability, okay, to have to provide a value, okay? It's like having curvification, okay, but on the context parameter level. So we have a context function with 2 context parameters. We provide only one. We obtain a context function with only the parameter that we didn't provide. Okay, as we said, changing the handler, the implementation and the handler, we can change the semantic. In fact, here we can implement, for example, a test handler for our random effect that returns always a fixed, okay, in this case, a fixed Boolean. And just to sum up, at the end of the word, we want to put the execution of the effectful computation at the boundaries of the system. We can run all the effects with the handlers and obtaining in this way the final result. So to sum up, does we adhere to the effect pattern? Yes, because we have a type that lists both the result and the effect accessed by the effectful computation. Okay, and the execution is deferred because we need the handler, okay, to run the recipe. Sorry, and we call the effect as capabilities. Okay, we can rename this kind of effect system as capability passing style. Okay, there is also another effect system called effect in Scala, which is a research effect system that uses the same name and approach that is very, very similar. And doing so, under certain, we almost have again our referential transparency, our local reasoning, and so on and so forth. Why I said it almost? Well, because we can't if we run an handler not at the boundaries of our system, we have a problem because we are running the effect. So we have to be careful about this. We can even add our effect system with an I/O, which means that we can defer the execution on a dedicated process, okay, and handling any exception that may pop up for any kind of bug. For example, we can use virtual threads. I remember you that from Java 24, we can virtual threads are completely safe because also synchronized blocks does not pinning the thread. So using virtual threads, if you are on the JVM, is a very nice option. But we have not finished yet. What if we want to reintroduce our map and FlatMap style, so our for-comprehension style in our effect system? Is it possible? Yeah, is it possible? Because playing some tricks with the Scala syntax, okay, we can define extension function directly on a context function. It's not that easy because we need to create a class type. Okay, it's the only way I managed to make it work. Okay, don't ask me why is it working, because I still didn't understand. But if we declare this class with the effect inside as a wrapper, okay, and we use it as the context parameter of our context function, and we rewrite a bit, okay, our effects using non-direct effect, but the effect wrapper in our class, we can return to have and rewrite our drunk flip function using a for-comprehension style, a monadic style. Okay, but what we obtain is still a context function. So we can use this directly in direct style, for example. And since we declare this function as inline, the compiler will translate this code exactly as the imperative, straight code that we all like. Okay? And so conclusion, just to sum up, so we define what is a side effect and why we don't like it. We define what is the effect pattern just to manage side effect. We saw how the current effect system are implementing the effect pattern, both with Uber effect and with algebraic effect. For example, we saw Kio, and we tried to build a small effect system to avoid using a monadic style, but then we saw that with that setup, we can reintroduce the monadic style and compare the two that with that setup are equivalent, maybe. Who knows? So, thanks for your attention.